now. Okay, so last week we met the axioms that we're going to be using, basically the axioms of set theory from our perspective. And the setting we're working in is designed to fit naturally alongside mathematics as you're used to doing it. So we have, so from last week, we have the universe that we're working with of all the mathematical entities that we can use to collect in our sets, so we can use as elements for sets. So we have a universe, and we have the notion, and obviously sets are going to be collections of the universe, but a collection of elements from the universe in general need not be a set. That was Russell's paradox. We had a theorem to that effect. So we have the general notion of a collection of elements of the universe, which is a class, a collection of elements from the universe. Have the notion then of a set, which is a special collection, namely one that is itself an element of the universe. So class that is an element of the universe. We were calling the universe U underlined. And in general, that is a collection of things from the universe. It's a collection of all things. In general, we're underlining classes. The class that is an element of the universe is a set. And then the point of sets is that we have, well, they're intuitively classes that are in some sense small enough to be a set. We went through some other intuitions last week, and they're governed by the axioms that tell us that certain classes do indeed form sets. The sets are governed by axioms, and the axioms we had last week were extensionality, empty set, pairing. Just to write them all down: powerset, separation, replacement, and lastly the axiom of infinity. We've said that the natural numbers are a set. And working within these axioms from now on, I'm going to do maths using the standard axioms that we have, which just fit alongside mathematics as we know it. So we're going to build on mathematics as we know it. So in particular, we'll use the set of natural numbers. And what we're going to assume, I mean, it's just our ordinary set of natural numbers that we're familiar with, but from our purposes, we're going to, so we'll use n for the carrier set of a distinguished, we had this notion of a natural numbers structure last week. So the natural numbers needs to be a natural numbers structure. But it's just, you can just think of it as our set of the usual set of natural numbers. So use n for a natural numbers structure. And once you have the natural numbers to hand, you can do the whole of mathematics. So as you're probably aware, there are straightforward constructions then of integers, which is normally often an integer is represented as an equivalence class of pairs of natural numbers, representing the integer that is the difference of the first from the second, or some such thing. So an integer is an equivalence class of such pairs. Then rational numbers are represented as equivalence classes of pairs of integers. selected pairs of integers, where the pair of integers is expressed as a fraction, and your equivalence relation says two fractions represent the same number, and it's a selected pair because you don't want the denominator, the number on the bottom of the fraction, to be 0. And then the real numbers can be constructed as in many ways, but for example, as Dedekind cuts, which are sets of down-closed sets of rational numbers satisfying certain axioms. And all of this you can look up in textbooks, or you can remember back to those of you who did the undergraduate course in degree program in mathematics. I guess this is like early material from the start of Annalisa Einer or something like that from years ago. Anyway, so from n, we're not going to dwell on this. We derive the integers, the rational numbers, and the real numbers, and many other things. And then there's this intuition that I've already mentioned today, and I spent time on a bit last week, that sets are, in a sense, classes that are somehow small compared with other classes. And that intuition is consistent with some facts about sets that are worth mentioning. So this is like sets as small in, I'm going to put small in quotation marks because how small, I'll think about that in a moment. So the two facts I want to point out, which are easy consequences of the axioms, are that suppose A is a set and B class, and we have a surjective function. So I'm just going to write this, but this double-headed arrow, I'll use this notation from time to time. That means a surjective function. I'm just saying we have a surjective function from A to B, but it follows then B. It follows that B is a set. So this was actually one of our axioms. Do you remember which axiom this is? Anyone remember? Replacement. Replacement. So the image of a set under a class function is the set. So because this is surjective, the image is the whole of the class B. So this is replacement. So it's consistent with the idea of sets as small classes because if mapping under a surjection, you're kind of making the set, the starting set smaller by squashing elements together by, if you like, quotienting. Although we're not saying this is the set of equivalence classes, it's just any surjective function. Okay, but it's a natural way of making things smaller. There's a natural dual approach to making things smaller. So one way of making things, the size of a set smaller is by squashing elements together, which is what we're doing here. And another way of making a set smaller is by carving out elements from within the set. So going to a subset. When one goes to a sub-collection of a set, one gets back a set. That's the separation axiom. But more generally, there's a dual property to this, which is suppose now A is a class this time, and B the set, so with the opposite way around. And we have, so this time rather than a surjective function, an injective function. And my notation for injective functions is going to be this. That's the notation that category theorists use for monomorphisms. So if we have an injective function, then this time round, sorry, A was the class, B was the set. So this time round, we're finding a class from within a set, and the class A is itself a set. Then A is a set. So this looks like the separation axiom, but the separation axiom merely tells us that the image, merely tells us that the image of this function in B, which is a subclass of B, is a set. And we need to transfer the fact that the image in B is a set to the class A. But they're in bijective correspondence. So again, we can use replacement to get us from the image here to the class A. So this follows from replacement, from separation and replacement. Okay, so it's a good intuition to have, but sets are closed under properties that you would expect small collections to be closed under these two properties. And it's a good intuition to have that sets are somehow small classes. But on the other hand, small does not mean finite, because we have the axiom of infinity, so we have an infinite set. We've got the power set operation. We can define function spaces. So we quickly have ways of iterating constructions that blow up the size of sets. And it's one of the starting points of this subject is really the fact that our axioms all encode reasonable constructions that we do every day on sets in mathematical practice, instructions that are used everywhere in mathematics. And as a result of those constructions, we cannot avoid being forced to include into our universe. And now we've got real numbers, the power set of the reals, the power set of the power set of the reals, sets that quickly get quite large. And in fact, as we'll see in the course, they get quite mind-boggling. So sets are small classes, but small really does need to be included in the context. Because small is small can still be very, very, very large. And so what we're going to do today is we're going to begin in thinking about how we talk about the size of sets. And because we're going to have sets of different, they're all small as classes, but we're going to have a very rich theory of sizes of sets. So today's topic is about the size of sets. That's the notion of cardinality. And really the beginning results on how one compares cardinality. So today's topic is comparison of cardinality. And the basic definition, this was one of Cantor's major contributions to mathematics. This was his idea. How do we say that two sets of entities have the same size? And Cantor realized, and it was a very innovative idea, and he was not sufficiently appreciated for it by the mathematical community in his lifetime. But his idea was to say two sets have the same size if they can be put in bijective correspondence with each other. So if there is a bijective function from one set to the other. So two sets have this. So what we say is have the same cardinality. That's one thing people say. Or another thing they say is are in bijective correspondence. And there's actually an official name for it. as just a single adjective. So they are, does anyone know what it is? It's similar in Slovene in Logica and Logica in the first year. Oh, you could say, yeah. Okay, we could say that, sorry. Or isomorphic. People wouldn't use that so much. I mean, yeah, it makes sense, although often you tend to use, in general mathematics, one tends to prefer to use isomorphism when there's also some other structure around. But you might say that. But the word I had in mind was equipotent. So this is a word that you'll find in set theory textbooks. But, you know, I somehow never hear mathematicians in the street talking to each other about sets being equipotent to each other. So it's kind of the officially correct word, but one tends to use one of the other phrases instead. Anyway, so this is the definition. Two sets have the same cardinality if, let's give the sets names, A and B. So if there exists a bijective function f from A to B. And that's it. And of course, you have a bijective function from A to B, you have an inverse, which is a bijective function from B to A. Simple facts like this, I'm also not going to dwell on. Except to say what the formal properties are, and just to say then, so this is going to be an important relationship, and the notation for this is, we write that the cardinality of A is equal to the cardinality of B. So I'm going to use this notation for the moment just to express that. So for the moment, we don't have an independent meaning for what, we don't have an entity that is the cardinality of A. We don't have a numbering system for cardinalities. But nonetheless, for any two sets, we can express this relation, and we write it notationally like that. Okay? But we don't need to define what a cardinality is. No. In a sense, a cardinality is an equivalent class of sets, and that makes sense. But there is no class of all cardinalities, because the equivalence class of sets that is an individual cardinality will not itself be an element of our universe, because it's not itself a set. So one gets into little issues like that, but anyway, one doesn't need to worry about when one uses this notation quite happily, as we're going to do. I mean, at least I should be happy. Hope you will too. This has some formal properties. These hold for all sets A, B, and C of the relationship of equipotency being of the same cardinality. So firstly, it's reflexive. Why is that? Because the identity is a bijection. It's symmetric. If A has the same cardinality of B, then B has the same cardinality of A. Why is that? Well, because if F is a bijection from A to B, and as I said, it has an inverse, which is a bijection from B to A, so that gives us the what we need, the opposite direction to hold. And unsurprisingly, the third property is going to be transitivity. So if A has the same cardinality as B, and B has the same cardinality as C, then A has the same as C. Hence, this relation of equipotency is an equivalent relation on sets. So lastly, as a single remark, why does it help? So A's same cardinality as B, we have a bijection F from A to B, we have a bijection G from B to C. How do we get to bijection from A to C? Defined by this. Simply composition. While clearing the board, just to remark, in English, there is no word compositum. So when you compose two functions, and in doing so, you get a composite, or people might also use composition as a noun, but that's the way to talk about compositions. Okay, so that's the equality of cardinalities. There's another very important relation, is the ordinary cardinality, when one set is smaller in size than another. We've already said there might be two ways of thinking about smaller in size. There might be squashing things down, so namely, if you've got a surjection from one set to another, that would be squashing things down. Or another would be living inside. So if you've got an injection from one set to another. It turns out the surjective notion is not a very good notion for building the ordered relation of cardinalities as the primitive notion. There are various reasons. It works better when you have the absolute choice. But the useful and fruitful, that which produces most interesting properties, notion of comparison cardinality is based on, say, one set has cardinality less than or equal to the cardinality of another if there's an injective function between them. So maybe I wish I'd left some of the text up because we could have reused it, but anyway, a set A has cardinality less than or equal to, I'd say this is very clumsy, but I don't really know a better way of saying it, or equal to a set B if there exists an injective function I say from A, B. The notation is we just use the usual smaller than or equals relation. Once again, there's still no independent at the moment, still no independent meaning to the cardinality of A as a concept in its own right, but we know what it means to define the verb. We know what it means to say that one cardinality is less than or equal to another cardinality. And the properties of this relation are again quite what one would expect to a degree, although some subtleties come in at the moment. So firstly, it's smaller than or equal to, so indeed it's reflexive. And again, the identity function works because that's an injective function. Of course, we're not going to have symmetry because it's an order relation, so we don't want it to be symmetric. Let's remove that. I wish I'd put that to the third property. We do want it to be transitive, and it is transitive. And the reason is exactly the same as before, because we have an injective function from A to B, F, and an injective function from B to C, G, then the composite G composed with F is again an injective function from A to C. It can't be symmetric, but it would be nice if it has the notion of expected of a partial order or anti-symmetry. And indeed that does hold, and that's a relatively deep result. I mean, it's something that was also covered in logic in the first year. It's a fairly famous theorem. It's called the Cantor-Schröder-Bernstein theorem. So it's been written out in the note. It was actually first proved by Dedekind. So it should be the Dedekind, Cantor-Schröder-Bernstein theorem. Bernstein is writing there because the nice proofs that people use nowadays was due to Bernstein.
I must make this something. Why doesn't it just follow from
Well, I haven't written down what it is, but it's the anti-symmetry property.
right.
So you know, there's a distinction mathematically between pre-orders, relations that are reflexive and transitive, and partial orders, relations that are reflexive, transitive, and antisymmetric. And that property is that if the cardinalities of A and B are mutually less than or equal to each other, then they have equal cardinality.
I just had this in back.
Yeah, but still, it doesn't look like a deep property because you might think, okay, yeah, well, we've got an injective function from A to B, and we've got an injective function from B to A. Why can't we compose them to get a bijection? They must be bijective, and why can't we compose them to get a bijection from A to B? And that's because the composite need not be a bijection. It's easy to find counterexamples to that. And what the theorem is telling us is if we've got an injection from A to B, we've got an injection from B to A, then we can conjure up some isomorphism, some bijection from A to B. But producing that's going to take some work. And that's why it's a theorem. And as I say, relatively easy. There's another property one might ask for, and that's that it's not just a partial order, but a linear order. So that would say that for all sets A and B, it either holds that A is smaller than equal to cardinality, has cardinality less than or equal to B, or B has cardinality less than or equal to that of A. And this is going to be true, but only when we assume the axiom of choice. That's going to be later in the course. This will be true. Don't worry, we'll be doing lots of things at a much deeper level than this before. We're not going to spend a long time getting to this result. It will just be a byproduct. But for the moment, we're going to, we'll leave this till later. So when we have the axiom of choice, we'll get this. But what I want to end this part of the lecture with is an outline of the proof of the Cantor-Schröder-Bernstein theorem to show you how one constructs it. So the proof I'm going to give is sort of quite along the lines of the proof of the arguments that's given. I mean, there are really very many ways of formulating this proof. I'm going to follow essentially the approach that's taken in the textbook by Krabicek and Jack. That's the main course textbook, because I find it the one that's most easy to visualize what's going on. I just want to make sure I set things up with frameways in the note. And the main work is going to go into the proof of a lemma. So the lemma is this. Which is, if we have two, so we're going to consider a special case where one of these sets is actually a subset of the other. And then we'll be able to still derive the result from we'll be able to derive the general case from the special case. So I'm going to formulate it like this, because the numbering is going to be useful in the proof. So B0 is a subset of A0, so B is going to be just the B part subset of the A part. And we have an injection from A0 to B0, so if the cardinality of A0 is less than B0, then A0 and B0 have the same cardinality. Okay. To prove that, let's let f be the name of the injective function from A0 to B0. We have such a function. And then we're going to draw a picture. We'll do the picture on this board. Maybe I'm going to try, so the details are in the notes. Maybe I'll see how much I can do just using the picture. So we need two colors for the picture. Let's use blue and red. So A0 is our large set, our containing set. I mean, I shouldn't use the word large because both sets are going to end up being the same size. So that's a very silly choice of word, but A0 is the containing set. Let's draw that as a square. And let's get a better blue pen for continuing afterwards, hopefully. Let's draw B0 as a sort of oval inside A0. And then we've got this function, injective function from A0 into B0. So if we map the whole of A0 along this function, we'll get the image of A0. And that's going to be, and because it's an injective function, A0 doesn't lose its shape as it were. No two elements get identified. So we get a copy of A0 inside B0, namely we obtain that as f of A0. So let's draw that looking like A0 inside B0, but we'll call this A1. This is A1. And so in general, we're going to define A m plus 1, B equal to f of A. Okay. But f's an injective function, so if you consider the subset of A1 that corresponds to the image of B0, well, you know, this is a picture of A0 inside B0, so to speak, translated along here. And so we get a copy of B0 inside that, which is at B0. So we get B1 inside here. So also, we'll find Bm plus 1, B. Here. And obviously, we can iterate this. We've got like this smaller copy of A0, which is A1, and we can apply F to that. So we get a copy of the same shape inside B1. So that's going to be A2. Definition still applies. Just using the general definition of A sub n, that n equals 2. So A2. And we do the same thing. We also look at f of B1 and get B2. And now, they're supposed to be the same shape, even though they're getting a bit lopsided in the picture. But we'll just draw dots, because you can, as you can imagine, that just carries on indefinitely. And now what we're going to do is we're going to name the parts. Let's do the yellow bits first in my picture here. I don't have a yellow on the board, so we'll do it in in orange. We're going to identify these parts which are B sub n, set difference A sub n. Sorry, the other way around. A sub n, set difference B sub n. So those bits of A0 that are in the boundary between between A0 and B0. So those bits that are outside of B0, and then those bits of A1 that are outside of B1. These are all the orange bits. We're going to call these. We're going to call these C. So to define C of n to be equal to A of n set difference B of n. And we'll just let C, which is what's shaded orange there, be the set of the union of all the C fragments. So C is the union over the n of the C events. And we're going to let D be everything that's in A0 that's outside C. So A0 minus O0. So D, right in green, is going to be A0 with D taken away. And let's shade the D parts here. Well, then this starts off as green in here, but then obviously, you know, you get an infinite number of iterations in this picture. But hopefully what you can see from this picture, that if we take all the orange parts, so f is a bijective function, sorry, f is an injective function, but any injective function is bijective from any subset of its domain onto the image of that subset under the function. So f gives us a bijective function from C0 to C1, and a bijective function from C1 to C2, and a bijective function from C2 to C3. And putting those functions together, we see that f, the set C, is closed under f, and in fact, that f, let's write it in black, f from whole of C to basically what it's doing is it shifts each orange ring, if you like here, with a ring with a square outside, one level down. This bijective function that if you apply it to the whole of C, that's to all the concentric rings simultaneously, or the orange concentric rings simultaneously, you'll get back the whole of C except for the outer. Each thing gets shifted down, so you just don't get back the outer one. So this goes to C minus C0 is a bijection. And then we have that B0 is the disjoint union, is the disjoint union of D, the green stuff, with C minus C0, all the orange stuff except for the outside part. So it's the disjoint union. So that's just the union, but I'm writing the plus to emphasize that there is no intersection between these two sets. But because there's a bijection between C and C minus C0, we can use that bijection to take us from here to here. So, so this is, let me use the isomorphism symbol. This right-hand side here is or let's put it here, this right-hand side is isomorphic to D, disjoint union C, and that is the same thing as A0. So we've ended up getting a bijection from B0 to A0, which is what we wanted. And more details are written in the notes. Okay. And once we've got the lemma, again, more details are written in the notes, but the theorem, the Cantor-Schröder-Bernstein theorem, is now easily proved because the proof of CSB. So now we assume that. Let me just start off as I refer to the notes just to avoid getting into some awkward notational issues. My advice. Oh. Okay, we're going to assume that A is. There is no apparently awkward notational issue. And we want to prove that these two sets have the same cardinality. So we have injective functions. F from A to B, and G from B to A. We're simply going to define B0 to be, we're going to define A0 to be A. That's our containing set here. We want a subset of A0 that has smaller than or equal to cardinality to such that A0 has smaller than or equal cardinality to B0. The obvious thing to take is just B0, we take the image of G. So image. So I'm just going to write this for image of G. And indeed, then G composed with F goes from A to B0 is an injective function. So indeed, cardinality of A0 is less than or equal to cardinality of B0. Hence, by the lemma, cardinality of A0 equals the cardinality of B0. And because B0 is the image of B under an injective function, that image is in bijection to B itself, with x equals to the cardinality of B. We're done. Okay. And with that, we are 1 minute behind schedule with the clock on the back wall, so we'll have a break until 16 minutes past. Okay, are there any questions? I shall pause. Okay. Right, so we've proved the Schröder-Bernstein theorem, the Cantor-Schröder-Bernstein theorem. We've been dealing in Cantor-Schröder-Bernstein theorem that if two sets are mutually in the order relation or cardinalities with each other, then they have the same cardinality. That is, you think of them as having the same size. And this proof here is the one that Bernstein came up with. So I think it's a very nice proof. It also is a pattern that's useful for proving other theorems. So later in the course, one option we might have is to potentially prove what's called the Barnard-Tarski theorem, which is a very strange consequence of the axiom of choice. We'll talk about it when and if we come to it. But the same proof as the Schröder-Bernstein theorem in a different setting, the same idea of the proof is actually useful in part of the ingredient in that result. And another place that the same proof idea comes up is in, so if you've done some measure theory, you may know that Borel sets, or probability theory, Borel sets are an important family of subsets of real numbers, but the Borel sets make sense in general for topological spaces. And in fact, there's a result that if you have a topological space that's can be given that's obtained from a complete metric space, and that metric space is separable, then any two such spaces always have the same lattice Borel sets. That's a rather deep result, and part of the proof involves this very, very similar Schröder-Bernstein style argument. So I've actually the picture on the board for that. And let's leave it on a bit further. So what we've got so far is we have the relation between two sets of having same cardinality and having cardinality less than or equal to that of another set. What other relations might we want to have on cardinality? Well, I think the other very obvious one is to have a strictly less than cardinality relation. So that the strict order on cardinalities but this is just defined according to a recipe that whenever you have a partial order, there is always a strict order associated with the partial order, and you simply define that by, well, the strict partial order is defined to hold. So the colon if and only if means defined to hold if and only if. Well, of course, you need to be in the non-strict partial order, but also we want it to be strict, so we want to forbid the equality from actually holding. So and they're not equal, which I'll write using here. I shall negate the equality relation using the obvious notation. So meaning there is an injection from A to B, but there is no bijection from A to B. Okay. And this has the expected properties. So of course, no set is in the strict order with itself. And the other important property, given that we already have the less than or equal relation, is that if we sandwich a strict inequality between some non-strict inequalities, we retain the strict inequality. And all other relations follow from this. So this implies that A is strictly less than D. Okay, so this is all very standard. But in this course, as I've already said a couple of times, we're not going to assume the axiom of choice until we're forced to, because I think maths without choice is also very interesting. And in the absence of choice, it turns out there's another relation that I call I think I call it the very strict order. Yeah, the very strict order. So it's a stricter order than the strict order. And this is terminology only in this course, the very strict order. No, you know, most people just assume the axiom of choice at the start, and these distinctions just don't occur. But you can find this relation in literature, just it isn't normally given a name, as far as I know. So very strict order. So very strict ordering of nullities. So here we're defining the cardinality is strictly below that of B if there's an injection from A to B and there is no bijection from A to B. Something stronger we could just ask for is that there's no surjection from A to B. And that's stronger because if there's no surjection, there cannot be a bijection because any bijection is a surjection. But the other implication cannot be proved without the axiom of choice. So it is, without the axiom of choice, a stricter relation. So let me just write that down. So I'm going to write a, like a numerical analysis. One uses this test, but very much below. A is very strictly below B, if and only if the cardinality of A less than equal to B as it has to be, but not just they're not equal, there is not just there's no bijection, but there is not even any surjection. So and there is no surjection from A to B. And the properties of this are, well, it's stricter than this, so it is, of course, irreflexive, but we can get that by the important property, which is that if A is very strictly below B, then it is indeed strictly below B. That's easy, just because any bijection is a surjection. And the other important property is the same as this one, only with the very strict relation in the middle. So, if A has an injection from A to B, if B is very strictly below C, and if there's an injection from C to D, then A is very strictly below D. And in the notes, there is a proof of this, where I prove, I consider the case for A, B, and C, prove that, and I consider the case for B, C, and D, and prove that, and then the two together give the whole result. So you can look at the proof if you want. It's a fun exercise to think about this for yourself. So it requires a bit of manipulation to prove these results. That's a good exercise in manipulating these relations. But although this does not really occur in the literature, in this course, to begin with, when we establish strict inequalities, we're going to actually establish very strict inequalities because we can, and it's stronger in doing so. And in fact, the proofs one gives of the strict equality typically give you a very strict equality anyway, as we shall see. Okay, so we now got the four relations, main relations we're going to have between cardinalities this course. So let's box them top of the board. And so we know how to compare cardinalities. But as I've said, this is independent of giving any, we haven't given any separate identity to what it means, what a cardinality itself is. We're now going to think about different cardinalities that sets might have, starting with the simplest case, which is, of course, finite sets. So,
just a very stupid question.
Yes, great. Stupid questions are the best questions.
I mean, I'm guessing that the cardinalities we're going to define are in the full sense, a quotient by these relations. But like, what's the size issue? Like, why can we just say the cardinals are the skeletal category?
Aha, right. Right. So there's a temptation to define the notion of cardinality as equivalence class of sets on the equality relation, as I said. And then there's an issue that there is no class of all cardinalities. So there is a sort of size issue there that one could avoid by changing the framework, like having some sort of superclass, notion of superclass or something, or bringing in some universals, what we'll actually do later in the course or something. But actually, we're not going to really worry about that too much. So rather, for the moment, we're going to consider cardinalities more on a case-by-case basis as they come up. And then eventually we will get the notation. Once we have the axiom of choice, we'll get a notation for all cardinalities using the Aleph notation. But that's all infinite cardinalities. So before that, one needs to finite cardinalities. And when you have the Aleph notation, then there's no problem about the notations. So we will get there. So actually, one could try to have cardinalities as equivalence classes, but we're not going to worry about that too much. Until we get Aleph, we're just going to use cardinalities with notation between relations like this. But sometimes we will have individual cardinalities in cases where we can easily define them. And we're going to do that. We're going to do that to begin with the finite sets. So we want to start classifying our cardinalities with the easy ones. We're going to start off with a finite set. But first, we need to define what is a finite set. Okay. So to define finite cardinalities, we need to define finite set. So I'm going to follow the same approach that's taken in the Logica and Logica course in the first year, undergraduate here, and do that by defining standard finite sets first. So a standard finite set defined to be, so for any natural number, I was about to write this, little n has type n, and then I remembered we're in a course on set theory, not type theory. So yes. Anyway, for any natural number with little n, we define the standard set with n elements just to be the set of all natural numbers n, such that n is less than, strictly less than n. So, for example, 0 is the empty set because there are no natural numbers strictly less than 0. Standard set 3 is the set of 0, 1, 2. And in general, the set square brackets n has n elements, and those elements are 0 up to n minus 1. So this makes sense, irrespective of which natural numbers structure we work with. If we work with the von Neumann natural numbers structure, then the set square brackets n will be identical to the number n, as it turns out. But that's irrelevant to doing mathematics. So this is a set. This definition makes sense in general mathematics. It is simply the set of natural numbers strictly less than n. And then we can define what it means for a set to be finite. Well, maybe I'll put this at the bottom of the put it here. So a set A is finite. Definition: if there exists a natural number such that cardinality A is the cardinality of the standard set of that natural number. So if the set A can be put in bijection with 0 up to n minus 1, some natural number n minus 1, or some natural number n. And then we define the cardinality of A above where n is as above. define the cardinality of A to be that natural number for which this holds. Why is this a good definition?
Because quality is good, that's really cool.
So you're saying because equality, the equality is
equality of
equivalence relation. Yeah, okay. But there's another more basic fact that's very important here, which is there's a unique n that satisfies this property. Okay, NB. So NB is a unique such n. And I just want to say a little bit about what one needs to do to prove that. And also, you know, we're basically supposed to be working from our axioms last week, and also what we need to do to derive this stuff from the axioms. So firstly, sorry? Oh, yeah, very good. What does NB mean? Who knows what NB means? Not a bene. It means note well in Latin, not a bene, which is used in the English language to say, please note this. So please, you know, take account of this fact. But yeah, it's an important abbreviation in the English language. But good, I should have said it. Very good question. So to begin with, how do we even define this? So here, what we're really doing is we're defining a function, wrap a natural number in square brackets from the natural numbers, and for every natural number, it's going to return a set of natural numbers. That's a subset of natural numbers. So we're mapping from the natural numbers to the power set of the natural numbers. And this is defined using the recursion theorem from last week by starting off with the empty set and using an appropriate operation involving a union as the operation that you iterate on. So the point is this, I won't go further into the details, you can work that out for yourself, but this is defined using the recursion. Last week. And then how do we prove this number's unique? Well, we need to prove a lemma, where the main bit of the proof involves a proof by induction. And the lemma is in the notes. So just need to find it. Oh, it's a proposition. In the notes, so the proposition, don't like this pen anymore. Is that all natural numbers m and n, the cardinality of m is less than or equal to the cardinality of the standard set for m with n elements is less than or equal to the cardinality of the standard set with n elements. That holds if and only if m is less than or equal to n. The natural number m is less than or equal to the natural number n. That's what we prove. And then it's clear that there's a unique n here, because if two standard finite sets are in bijection with each other, then one is square brackets n and one square brackets n. We have this relation in both directions, which implies n is both small and equal to n and n is small and equal to n. So they must be equal because of the properties of the order relation from the natural numbers. And this implication is trivial, because if m is less than or equal to n, it's very easy to define an injective function from this set to this. But this implication is not trivial. And it's a very good exercise to prove this from first principles. The first principles means we've got a natural numbers structure, and what mechanism do we have for proving properties of a natural number structure? Induction. So to prove this by induction, and there is the proof is actually given in the lecture notes, so you can have a look at it there. But just to say, you know, this kind of stuff is fiddly, and it's a sort of like fiddly level of kind of from a high school student going into mathematics at university or that kind of thing. It's not deep. But still, it's a good exercise to make sure that you're sort of happy enough doing this sort of thing. We should say there's a M&M here on natural numbers. That's the first property we want to prove. Another property is that for all natural numbers, the cardinality of the standard finite set is strictly less than the cardinality of natural numbers. That's something else what we want to prove. So for that, you exhibit an injection very easily, and it's just the identity, just the inclusion. But you need to show there is no bijection. Once again, you need to prove that by induction. But of course, not just there's no bijection, but there's no surjection from the standard finite set of natural numbers. So in fact, in this course, we will strengthen that statement to a very strict order. But anyway, the more important thing is that if this property is needed to show that the definition of cardinality, so we're defining the cardinality, we've got a definition of a finite set, we defined the cardinality of a finite set. So this property is needed to make sense of that, the cardinality of a finite set. And this property is, of course, very important because it's showing that all finite sets have a strictly smaller cardinality than the natural numbers. So two other general facts about finite sets. So I said sets are a kind of smallness notion. Sets we think of as sort of small classes. And finiteness is another kind of smallness notion, obviously a much more reasonable, really small, although no, finite sets can be very large, like the number of particles in the universe or something like that. That's I guess a finite set, but probably. Anyway, who knows? But anyway, finite is a sort of it's small compared with infinite. So it is a smallness notion. And just to point out that our definition of finite enjoys these two characteristic properties that we had also of smallness notions that sets enjoy. So finite sets enjoy if we have A finite and surjective function from A to B, then B is finite. And if we have B finite and an injective function from A to B, then A. And once again, to prove these from first details takes a bit of work. But it's obviously very intuitive. This is saying the image on a finite set is finite, and if you have a set of beds in a finite set, it's also finite. But proving these from this definition, it's a good exercise. If you like doing proofs from first principles, then I should go at this. Okay, just one other thing to say about finiteness. This is quite a convoluted definition of finiteness. First, we define what the standard finite sets are. Then we define finiteness in terms of being in bijection or being equipotent to one of the standard finite sets. And to get it going, we need to use the natural numbers structure in doing so. It is actually possible to define the property of finiteness of a set in a way that does not refer to the natural numbers structure at all. So if you're interested in that, you can ask me about it in the break, but I don't want to spend time in the lectures, but I may try to encourage Gregor to do this in the exercise class next week. But it's something quite interesting to try and think about yourself. How might we define the property of a set being finite without referring to the natural numbers? It's not obvious, but it can be done. Okay. So we've got finite, and we've seen that natural numbers itself is not finite by this statement here. So this implies n is not finite. So the natural numbers are not finite. But the set is not finite, or the natural numbers, would you say the natural, yeah. It's better to say n is not finite because every natural number is finite, of course. So set n is not finite. So let's define what is meant by an infinite set. So while I'm clearing the board, does anyone want to propose a definition of an infinite set? How would we define the set A is infinite?
So it's at least like the natural numbers. So we have an engine.
Oh, that's okay. Yeah. Okay, so we're going to have a definition. A is infinite. Definition if, and then once we've got the definition, let me just see whether I call it a theorem or a proposition in the notes, just to be consistent. I'll never remember these things. This should, yeah, I was hoping this would be a theorem. I think it's deservedly a theorem. But the following are equivalent. So this abbreviation means, no, actually, there's going to be an interesting relation between the following. Consider the following. And the first condition is going to be A is infinite. They're going to be related to each other. These are almost different ways of saying the same thing. And property 4 is going to be your definition, Yuri. Cardinality of n is less than equal to the cardinality of A. Right? So you've got a more basic way of saying infinite. Not finite. Very good. Yeah. I mean, we define what it means for set to be finite, so let's just say infinite is not finite. It is not finite. There is no, it is not in bijection with any standard set. And the second and third properties here are going to be, the second one is there exists. Actually, I'm going to talk about X rather than just to be consistent with the notes. The set X is infinite. There exists a proper subset such that X prime still has the same cardinality as X. So we can remove some elements from X and still not change the cardinality. Okay, so you clearly can't do that from the finite set. And thirdly, there exists a proper injection from X to X. So an injection is an injective function. Proper, can anyone imagine what?
Image is not.
Its image is not the whole set. So injective function whose image is not the whole set. Right, I want to put this in the box because it's the definition of infinite. And I also want to tell you that property 2 is a famous alternative definition of infinite proposed by Dedekind again. You say Cantor was a great contributor to this subject, and around the same time Dedekind contributed lots of stuff too. So this is called, so this says that X is Dedekind infinite. Okay, the theorem says, consider the following. That's not much of a theorem. So the result is going to be more or less that all the properties are equivalent. So let me state that now, but I'm going to improve it slightly later. So then, so 1 is equivalent to 2, is equivalent to 3, equivalent to 4. But this, as I say, this is a temporary statement of affairs. Now, in the notes, I have a comprehensive proof of the correct statement of affairs. In the lecture, you know, these are also things you can enjoy proving for your, you know, I'm assuming many of my remarks and suggestions for what you're going to do in the intervening week between now and next week, I'm assuming that you enjoy doing fiddly little proofs involving inductions and things like this, or manipulating sets. So that, you know, the proofs are in the notes, and you can try and do some of these for yourselves. I just want to focus on, you know, in essence, suppose we were going round in the circle. Let's do the very last implication we were getting. Let's go from 4 to 1. So this is the one I want to focus on as the interesting one. Hang on. No, what I want to focus on is the proof of 1 implies 4. So let's assume we were going around in the other direction. Anyway, this is one of the natural implications. Here, one wants to prove the more natural of the implications, and this is one of the natural ones to prove. 1 implies 4. So, suppose X is infinite. And we want to define an injective function from the natural numbers to X. Because that's how we prove cardinality inequality. So we need to define, an injective function from N. Right, I just want to check the notes for notation. So we're going to do that. So what is an inject? what's a function from the natural numbers to a set? Well, it's an infinite sequence. And an injective function is an infinite sequence of distinct elements. Okay. So we define an infinite sequence x sub n of distinct elements x. We essentially do this by reduction, if you like, or by let's make it. It's actually defining a function, so it's kind of using the recursion. I'm not going to. I just want to do it using sort of the informal way we do it in mathematics. So let's suppose the sequence x sub I from where I ranges from 0 up to n is already given. So this is like our induction hypothesis. And we start the proof, n will be 0. And because there are no i's strictly less than 0, this will be the empty sequence, which is already given. And then given that, so we can assume we've got strictly less than, so we've got the n elements of the sequence, and we want to find the element that's going to be x sub n. Okay. So since x is infinite, the function that maps an I to xi from, well, these, so this is defined for all I strictly less than n, but that goes from the standard finite set for n. That's exactly the domain of such i's for x. Well, because it's infinite, this can't be a bijection. And it's an injection, it's an injective function, so it can't be surjective. If an injective function is surjective, that's exactly the definition of a bijection. So the injective function, because they're all distinct, is not surjective. So we simply choose. X sub n to be some elements in x minus the set of all x sub i's that's in the image of this function. So 0 is less than I, less than n. And then we're done. We've defined xn. This is, by definition, this is distinct from all the previous ones. So we're maintaining the property of distinctness, and we carry on. Okay, so the above defines a sequence, an infinite sequence, by induction on n. So we're defining an infinite sequence, xn. Hence, this gives the required function and that required injective function. Okay. However, this proof does not go through from our axiom. Does anyone know why? Sorry?
Axiom.
Yes. What are you going to say? Yeah. So in fact, because we're choosing an element here, and we're making infinitely many choices as we go along, then we are using some aspect of the axiom of choice. So in fact, all these three are equivalent. And whoops, that was the problematic one. They all imply being not finite, but requires, let's for the moment put the axiom of choice, which we haven't got in our axiom system yet. But after the break, we're going to refine this to something. Now, this is what the sort of choice required here is much more innocuous than the kind of choice that's used, for example, in the Barnard-Tarski theorem, for those of you who have that. So what I want to start with after the break is looking at why, naming the choice we're using here and defining it formally, and we're going to the full axiom of choice we're going to see later in the course, but we'll look at what choice we actually use in this quiz. Okay, are there any questions before the break? Right, so we're actually 2 minutes early by the clock on the back wall, so we'll start at 13 minutes past by the clock on the back wall. Okay. Okay, so during the break, there was a suggestion for a potential definition of finite set not involving the natural numbers, and the actual definition given I didn't fully understand, and so I shall think about that. But just when that suggestion was made, I then realised that actually that question looks from this proposition, like from this theorem, as though it has two simple answers, because one could define finite to be the negation of 2, which does not make use of the natural numbers, or the negation of 3. 3 does not make, and anyway, 2 and 3 are equivalent to each other. And if you do that, you're defining you're rather than defining finite, you're defining not Dedekind infinite, which is not the same thing unless you have some form of the axiom of choice. So the real challenge is to define finite, not using the natural numbers, in a way that's equivalent to this definition of that's infinite, but in a way that's equivalent to the earlier definition of finite, without the axiom of choice. Okay, so this proof uses choice in some form because I use the word choose here just to emphasize it, and we're making infinitely many choices, so it requires some choice. But how much choice does it need? It does not need the full axiom of choice, and there are various or many flavors of the axiom of choice. In fact, the implication from 1 to 4 requires a simple version of choice called countable choice. And that's easy, countable choice. Which is an axiom we will also consider later in the course when we treat choice in more detail. This proof does not go through with countable choice. This proof requires something stronger than if you use what's called the axiom of countable choice, you need a cleverer proof, a more involved proof. This proof uses an axiom called dependent choice. So our proof, so it requires countable choice, but our proof of 1 implies 4 uses what's called DC, right at the bottom of the board here, I'm writing this, which is called the axiom of pendant choice. So I'm going to just write the axiom of dependent, just so you can relate this proof to a formal axiom. I'm going to write the axiom of dependent choice down. Also, because although we can leave the full axiom of choice until much later, dependent choice will be useful on numerous occasions before we get to the full axiom of choice. Dependent choice is my own favorite choice axiom as well. Yeah. I like to flag it early in the course. So the axiom of dependent choice DC, it's called. So it says if we have a set X and we have a binary relation on the set X. So a binary relation is, as we know, I hope, a subset of the product of X with, I mean, on the set X, it's a subset of the product of X with itself. If this enjoys the totality property, is total, so i.e. for all elements little x of the set X, there exists an element little y of X such that X is in the relation with Y. So I'm using your standard relation style here. So it means the pair X, Y is in the set R. Then, for any element x0 in X, there exists an infinite sequence xn indexed by the natural numbers. So this means a function from n to x, the same thing as a function from the natural numbers to x, such that x0 is x0. I've already called it x0, so never mind. Such that for all n, x of n is in relation with x of n plus 1. All natural numbers. But it's dependent choice in the following sense that we start off at x0, and from x0 we can obviously find an x1 because by this totality property there is some element of the set that's related to x0. So we'll choose one of those for x1, and then from x1 there's some element x2, again by the totality property related to x1. But at each point, at each index, we need to choose the next one because we're just told there exists some and we have to find them. There's no method of getting it. And when we gather those all together into an infinite sequence of choices, that's the dependent choice. And it's dependent because the choices we get, the choice at stage n plus 1 depends on the choices at previous stages because that's taken down us down the path that gets to that point. Okay, so that's the axiom of dependent choice. And here we're using it. I mean, the way I wrote it doesn't make it seem like we have a relation. But the relation here is on finite sequences of distinct elements from the set X. And a finite sequence is related to another finite sequence if the second sequence extends the first sequence by adding one more distinct element to it. Okay, that's how we started with the empty sequence here, and then the path through the set X will keep on adding a new distinct element. Okay. So that's how we get that from dependent choice. So I'm not going to assume this as a basic axiom. Our axioms are the ones from last week, our basic axioms. But occasionally we will use dependent choice, and then I will flag when we're using it, and then eventually later in the course we'll be using choice, full axiom of choice. And again, well, at some point we will assume the full axiom of choice, but not for a while. Okay, so far we have the definition of finite. We have the definition of infinite. We know that all the finite numbers are smaller than the natural numbers, strictly smaller, very strictly smaller. And we know that the natural numbers are smaller than all Dedekind infinite sets, which are all infinite sets if we assume the axiom of dependent choice, or even countable choice. So now we're going to start on the project of classifying. We have the notion of cardinality for finite sets. The cardinalities are just natural numbers. We're now going to start giving cardinalities to infinite sets. Okay, so smallest Dedekind infinite set is the natural numbers. Eventually, we're going to use Aleph cardinalities for all infinite sets. So we might as well start using that notation now. So we're just going to have a notation for the cardinality of the natural numbers. We just define, this is our definition of Aleph 0. So define Aleph 0 to be a name, if you like, for the cardinality of the natural numbers. But Aleph 0 is not going to be the cardinality, just the cardinality of the natural numbers. It's going to be the cardinality of very many infinite sets, and those infinite sets we give a name to, we call them the countably infinite sets. So a set X is countable, definition, if, well, so that there's some disagreement in the literature about what countable means. So in the Vrabacek and Jeff textbook for the course, countable means an infinite set that's in bijection with natural numbers. But a lot of people in mathematics use countable to also include the finite sets, and I prefer that because countable or finite always sounds very funny to me, and you can certainly count your way through a finite set. Well, plenty of people in mathematics use this. So for me, a set is countable if the cardinality of X is less than or equal to Aleph 0. What does this mean? Well, it means we basically replace this by the statement cardinality of, this is just a replacement for cardinality of the natural numbers. Doesn't need to have an independent existence as an entity in our mathematical universe at the moment. And so this is the statement: there exists an injective function from X to the natural numbers. That is that statement. If X is also infinite, we call it countably infinite. So if it is countable and if X is countable and infinite. And of course, the other important concept is that of being an uncountable. Uncountable is just going to be, well, just like infinite is not finite, uncountable is going to be infinite. Well, no, sorry, it's just going to be not countable. Yeah. So that's already implies in. So if X is false, countable. And as you know, countable sets are closed under many operations on sets. So, well, this is all right, isn't it? So obviously the natural numbers, the integers, the rationals, natural numbers times the natural numbers. And hopefully you've all seen proofs of these kinds of things in other courses. In the notes, there are some quick proofs of statements like this, where a very simple way of proving such statements is to use the Cantor-Schröder-Bernstein theorem, which means you want to show sets are in bijection with the natural numbers. You don't need to find the bijection. All you need to do is produce an injective function in each direction. Then the Cantor-Schröder-Bernstein theorem, proved by Dedekind, will give you the bijection without you having to do the painful work of coming up with bijection yourself. So more generally, countable sets are closed under finite product, disjoint union, disjoint finite union. And many other things. And I just want to make one other, I suppose two other, but it's the same point again that I've emphasized before. The countable sets. So once again, countability, because we're including finite, is a smallness notion, bigger than finite, but smaller than being a set. So also, if A is countable and B is an image of the function whose domain is A, then so we've got a surjective, so again the double-headed arrow, meaning there's a surjection from A to B, then B is countable. And the dual thing, if B is countable and there's an injective function from A to B, then A is countable. Countable, as we might expect, is a smallest notion. And of course, as you know, real numbers are not countable, they're uncountable. The power set of natural numbers is actually equipotent with the real numbers. So it is again uncountable. And this is an instance of a final result today, which is a very simple result, but it's one of Cantor's big contributions to mathematics. So it's Cantor's theorem that every set has strictly smaller cardinality than its power set. The power set always increases cardinality of the set. So our set of the natural numbers is immediately from that uncountable. Then you can prove that the real numbers are uncountable by establishing a bijection between the real numbers and the power set of the natural numbers. Again, that's most easily done by constructing injective functions in both directions. And then the Cantor-Schröder-Bernstein theorem does the rest for you, the rest of the job for you. So we have uncountable sets, but we don't just have one kind of uncountable set, because if we take the power set of the real numbers, we then move up to another level cardinality. So we're not going to go all the way to 5 o'clock today, because it won't take that long to state and prove Cantor's theorem. So I'm just going to do this, try to do this as efficiently as possible. The nice thing is the proof applies equally well to finite, well, a nice thing. I mean, the theorem is most interesting for infinite sets, but it's a nice fact that the proof applies just as well to finite sets. The theorem, the Cantor's theorem, nobody else has ever put their name on this theorem as far as I know. I mean, everyone knows this is Cantor's theorem. So for any set X, X has strictly smaller cardinality than our set of X. Okay. And I'm going to modify this statement in one way. Can anyone guess what it is? I already hinted at it. Sorry?
Strictly less.
Yeah, the very strictly smaller. Because we have this even stronger notion, and it's just the usual proof. Just the usual proof establishes very strictly smaller rather than strictly small. So, cardinality of any set X is very strictly smaller than the cardinality of its power set. And you know, here we're still in the realm of stuff you did in Logica in Logitech. I think so. From next week, things are going to be really new on this course. But this is kind of the end of Logica in Logitech. There's proof, and one even gets gets examined on this in Logica in Logitech. So you will have seen this proof before. So let's just do it quickly. So firstly, let's show that it really is smaller than, less than or equal to. So we just need an injective function. And what's an injective function from X to its power set? Well, there's a very simple one. Simply take any element of the set X and map it to the singleton subset. And that's obviously an injective function. So it remains to show the further condition for being very strictly smaller, which is that there is no surjective function from X onto the power set of X. So we want to show there is no such function. So as usual, we assume for contradiction there is such a function, and we'll prove that we get into a contradiction. So suppose, to show very strict relation, suppose for contradiction that, now to be consistent with the notes, I want to remember what I call this function, maybe G. Yep. We have a surjective function from X to power set of X. And now what we're going to do is we're going to define a subset of X that by its definition can't be in the image of this function. And then we've got a contradiction because this function is assumed to be surjective. So we define, and what do I call it in here? So define S to be a set of elements of X such that X is not an element of the set that G maps X to. And so by definition, S is an element of the power set of X. And also, for all elements of of the set X. We have that X belongs to S if and only if X does not belong to G of X. So in particular, okay, yeah. So now we use the surjectivity of G. So because S is in the power set of X and G is surjective, there must exist some little y in X such that G of Y is S. So by surjectivity, there exists some y, little y in X in the set X such that G Y is S. But then we have a very easy contradiction. Y, if you look very much at Y. So we then have a very easy contradiction because Y belongs to G of Y. If and only if, by this, Y belongs to S. If and only if, by this, Y does not belong to G of Y. That's a contradiction. And the only assumption we made was that we got a surjective. Oh, yeah, very good. The assumption was that this is surjective. Yeah, then we have a surjective function. I'm just going to use that double hyperbaric. The contradiction, therefore, no such G exists. So indeed, the cardinality of X is very strictly below the cardinality. Right, jolly good. So, as a corollary of that, the power set of the natural numbers is uncountable because it's not. It cannot have the same cardinality as the set of natural numbers. So I think, I mean, that's the end of the notes. Obviously, there are many details with like these proofs for induction that I didn't think it was a good idea to go over in the lecture, and because of that, we're finishing a little bit early today. But I think that's enough for today's material. And yeah, from next week we shall start doing stuff that goes beyond finally your first year course on logic and logic. Are there any questions before we finish? Okay, so thank you very much. Have a nice week and see you next week. Bye-bye.